Okay, this is unit test 3. Okay, so in the first problem, we assume that we have two coils here. We assume that the well, we don't assume. We're told that the switch is closed and has been closed for a long time. So this current through the wires through coil 1 has leveled out. If you look at coil 1 current with time on the side, when the switch is closed, the coil ramps up. It's steady for a long time. So that means the magnetic field inside this coil is steady for a long time, and it's going to point in that direction. The reason I know is because I point my fingers in the direction of the current. The current goes from positive to negative, so the current is up here. I point my thumb in the direction of the current, wrap my fingers in the direction of the magnetic field. It points inside the solenoid, and the outside is going to curve like that. Okay, so some of this field is going to pass through the second coil. The problem is we are in this region where there's no change in current. So there is no change in the magnetic field, so there's no change in the magnetic field through this coil. So according to Faraday's law, nothing is happening over here. But this question asks which is true if S is suddenly opened. So this is now back open again, and the current through that coil drops off. So that means this magnetic field drops off. So that means this coil must induce a magnetic field that tries to reinforce it to resist the reduction in the magnetic field. So that means if I look at the current on this line, the current passes upward through this wire, and I wrap my fingers in the direction of the magnetic field that's in the same direction as the field produced by this. So that's the direction we want, because we're trying to, this induces a field that reinforces this field, which is reducing. Keep in mind these coils are wrapped in opposite directions, as we can tell from the drawing. So the current's going to go that way, up through, down, and then back around. So let's look at our options. There's no induced current through R. Yes, we know there is. There is no induced magnetic field in coil 2. Of course there is. There is an induced current in R that flows from right to left. No. There's an induced magnetic field in coil, because we're traveling from left to right. Option D, there is an induced magnetic field in coil 2 that points towards C. No, because that's pointing in the opposite direction. We need to point in the same direction as the first magnetic field. So the only option, there's an induced magnetic field in coil 2 that points towards B in this direction. So our next question says, assume S has been closed for a long time. Which of the following statements is true if coil 2 is moved towards coil C? So what's happening there is we're taking this coil and we're moving it away. As we move away, these field lines are getting farther and farther apart, meaning the field from this coil is getting weaker. So this switch stays closed. We're not changing the current through coil 1, but we are changing the field because we're moving this coil away. So the exact same thing happens. There is a field that is induced that tries to reinforce the field in this direction. And so that is option A. There is an induced magnetic field that points towards B, the same as, the same as in question 1. Okay. Okay, question 3. We have a transformer with 120 volts across the primary and 1200 volts across the secondary. If the secondary coil has 800 turns, how many turns does the primary coil have? Okay, so the P equals 120 volts. The S equals 1200 volts. The secondary coil NS is 800 turns, and the primary is, we don't know. Well, you have an equation for this. You have, you know this ratio. NS over NP equals VS over VP. let's see. So we're solving for NP. I just multiply each side by NP. So now I have NP Vs over Vp equals Ns. And I'm going to multiply each side by the reciprocal, Vp over Vs. Np equals Ns Vp over Vs. When you plug in the numbers, it comes out to 80. And when you had this test, I didn't give you the multiple choices, but you know, this version has it. You will not get multiple choice on the final. Well, some, but not always. So which of the following units results when calculating this quantity? Well, first of all, you have to know what this quantity is, and this quantity is capacitive reactance. And of course, that's measured in ohms. Which of the following graph illustrates how capacitive reactance varies with frequency? Well, if we think about this from a theoretical standpoint, if you have an AC generator that's moving current back and forth, the faster it switches directions, the less charge can accumulate on the plate. So therefore, the resistance is very little at high frequency. And at low frequency, basically you're approaching the DC situation where the charge builds up for a long time and you have a big resistance to putting more charge on the plates. So therefore, the capacitive reactance is really high. That would be option 5. The current in a certain AC circuit is independent of frequency at a given voltage. Which combination of elements is most likely to comprise the circuit? Well, if it's independent of frequency, there's only one component that's independent of frequency, and that's resistors. It doesn't matter what the frequency is with the resistor. The resistance is the resistance. When the frequency of an AC circuit is decreased, the current in the circuit increases. Which combination of elements is most likely to comprise the circuit? Well, let's think. It can't be resistors because we said that's independent of frequency. It's going to be inductors. If the current in the circuit increases, the inductive reactance decreases, because if you remember XL over frequency, it has the linearly increasing equation. So as the frequency is decreased, inductive reactance decreases, so the current then can increase. Could it be capacitors? It can't be capacitors because we know it has the opposite trend. Could it be capacitors and resistors? Well, no. Could it be inductors and capacitors? It could be, but the problem, if you had inductor and capacitor, XL plus XC, then you would have that familiar impedance graph. And so, yeah, as you decrease frequency, the current would increase. The current would look like this. The current would increase, but then it's going to decrease again. So that's not a good option. This is most likely the situation. Okay, for the next two problems, it's a little bit grouped a little bit differently on here, but it's the same content. I'll step you through the whole thing. Okay, so you have an RLC circuit. If you draw the circuit, it's going to look like the resistor, the capacitor, and the inductor. So if I were to draw the first question says what's the impedance, I'm going to do this by drawing the phasor diagram. If you remember the phasor diagram, so I'll draw the current, looks like this. This is the current. This is the voltage over the resistor, which is always in phase with the current. This is the voltage over the inductor, which leads the voltage over the resistor, which leads the current, I should say. And this is the voltage of the capacitor, which also leads the current. So there's going to be some resultant, some total voltage of the system. And let's see, the capacitance is greater, yes, the capacitance is greater than the inductance. So we know it's going to be somewhere down here. And then phi is the angle between them. So the phase angle then, if we were finding the phase angle, so tangent of the phase angle phi is going to equal the opposite side of this triangle, which is opposite to the angle phi, which is VL minus VC, over the adjacent, which is VR. And so phi is then equal to the inverse tangent of VL minus VC over VR. That is the phase angle, if we were to find that. And that turns out to be negative 55 degrees. So what is the impedance? Well, the impedance is, let's relate all these things together. So the total voltage is equal to, that's the hypotenuse of this triangle, is equal to VR squared plus VL minus VC squared. That's the other side of the triangle. VT is just equal to IZ, that's Ohm's law, where Z is impedance. And this is equal to IR squared, quantity squared, plus XL, IXL minus IXC squared. The I drops out everywhere, so impedance then is just equal to the square root of R squared plus XL minus XC squared. If you calculate that out, that comes out to 349 ohms. So what is the RMS current in the circuit? Well, that's just, as we said before, that's just equal to IZ, or I is equal to VT over Z. And we know VT from this stuff. VL minus VC squared, because we have the voltage across all these elements. So you can do it like that, and then you can just put in 349 ohms. I then equals 0.430 amps. And question number 10 says, what is the average power consumed by the circuit? Well, here we have to know that average power is I squared R. Only the resistor matters. So that's the tricky part there. You just have to know that the resistor matters. The impedance, the impedance does not, because there is no power dissipated over the capacitor or the inductor. So the average power then is equal to 37.0 watts once you plug in the numbers. Okay, so what is the phase difference between the voltage across the capacitor and the voltage across the entire circuit? Well, if you look at our phasor diagram, we know phi is equal to 55 degrees. That is the voltage between VT and the current. But we want to know about VC, which lags the current by 90 degrees. So we want to know what this angle theta is. Well, theta is going to equal 90 degrees minus phi. So that equals 35 degrees. And I'm just looking at the absolute value of phi. So the angle is 35 degrees, and it lags, VC lags VT. VC will always lag VT, right? Okay, which of the following statements concerning the wavelength of electromagnetic wave in a vacuum is true? Well, the wavelength is inversely proportional to the frequency of the wave. We know that's true. Well, the wavelength, let's go to the others. The wavelength is independent of the speed of the wave for a fixed frequency. Well, no, it's not. The wavelength is inversely proportional to the speed of the wave. No. Same for all types of electromagnetic waves? No, because that's what defines the difference in them. It's directly proportional to the frequency? No. So there's only one option that works. Complete the following sentence. The various colors of visible light differ in both frequency and wavelength, because as frequency varies, so does wavelength. When a radio telescope observes a region of space between two stars, it detects EM radiation that has a wavelength of that. The radiation was emitted by a hydrogen atom, blah, blah, blah. What was the frequency of this radiation? Well, you remember that frequency times lambda equals the speed of light. And the question's asking for frequency, so that's c over lambda. You plug in the numbers, you get 1.43 times 10 to the 9th hertz. All right. What would the speed of an observer be if a red traffic light appeared green to the observer? Okay, so it's this. The observer in his car is traveling with some velocity towards the light. So the velocity of the observer, we don't know. The frequency of the source is 4.688 times 10 to the 14th hertz. The frequency to the observer is 5.555 times 10 to the 14th hertz. So let's use our Doppler shift equation. FO is equal to Fs times 1 minus V over C. And you can call that V of the observer if you want. So then it's just a matter of solving algebraically for velocity. FO over Fs equals 1 minus VO, 1 over VO minus C. So VO over C is equal to 1 minus FO over Fs, and VO is then equal to C times 1 minus F naught over Fs. Once you plug in the numbers, that then equals 5.55 times 10 to the 7th meters per second. And that was the last question for the unit